Hey there, this is problem number 50, and it wants you to give a strategy that allows you to find the speed of a mass when it's halfway to an equilibrium position. And they set up the problem first by you have just a brick wall here, so we'll just, or whatever wall you want to have. And we've got a spring that's attached to the wall. That spring then is also attached to a mass, and that mass is 0.4 kilograms. You go ahead and you move this thing to the right, and when you do that, you stretch that spring out even more. And so here's our same mass again, which is 0.4 kilograms, and it's released 3.2 centimeters from this position. So we're going to go ahead and make our distance from this point to this point 0.032 meters. Remember, we don't want to use centimeters there. We know the spring constant for the spring is equal to 26 newtons per meter. And they want us to find the speed at a point halfway between the 2 points that we see there. So we really want that speed. We're going to number these. This is position 1, position 2, and finally the position in question, which is position 3. So let's go through and figure out the energy, and let's do that at both position 2 and position 3. Position 3, please notice that from equilibrium, the distance here would be 0.016 meters because it's halfway in between. Our potential energy at position 3 plus the kinetic energy at position 3 should be equal to the potential energy at 2 plus the kinetic energy at 2. We know there isn't any kinetic energy at position 2 because that thing is not moving at right here. So it's stopped at an instant. And all we will have at that point then will be this potential energy. Potential for energy for a spring is just 1/2 kx squared plus, and then here's our speed, 1/2 mv squared. And that should be equal to the potential energy at point 2. So what we'll do is we're going to put a 3 for this x, and then we're going to say 1/2 kx2 squared since it's at position 2. Those are going to be two totally different numbers. Our halves, we can just get rid of all the halves, and now we need to solve this equation for v. Let's go ahead and rearrange it. We're going to say mv squared is equal to k x2 squared minus kx3 squared. We could factor out the k's, and we can divide by m, so v squared is equal to k, and then we can put x2 squared minus x3 squared, and we can do that over m. And at this point, we could just say that v is equal to the square root of k times x2 squared minus x3 squared. And we're going to go ahead and just divide that by m. Let's go ahead and plug all of our numbers in. So this would be the square root of k is 26. x2, remember, is our distance at position 2. So that's going to be the full 0.032 meters squared. And then we need to subtract that. We need to subtract off the distance at 3, which would be 0.016 meters squared. So I'll go ahead and put that in brackets, not to confuse anybody. And then we'll divide that by the mass, which is 0.4 kilograms. When you get done, you should end up with a speed of 0.22 meters per second. And remember, that speed is happening at this point right here. Okay, the speed at this point is equal to 0, and just as a side note, the speed at position 1 would be equal to the maximum speed because that's where it wouldn't have any kinetic energy. So that is the solution to number 50. Let's move on down and take a look at the next one, which is number 60. It says a simple pendulum of length 2.5 meters makes 5 complete swings in 16 seconds. Remember, a swing for a pendulum would be you're actually going to start the pendulum here. It's going to swing all the way over, and then it's got to come all the way back. And so that would be equal to 1 complete swing. And that would also, could also call that 1 cycle. So it's got to go all the way over and all the way back for that to happen and for that to count. So it does 5 of those complete swings in 60 seconds, 16 seconds. They want to know, what is gravity? What is the acceleration of gravity at the location of the pendulum? Our equation for the period of a pendulum, so we'll do TP instead of TS, is equal to 2 times pi times the square root of, and then it's the length of the pendulum divided by gravity. Notice that mass does not matter here. So we don't worry about the mass that's hanging on the end of the pendulum. You have to have a mass, but it doesn't matter what that mass is. So you could use a ping pong ball or a bowling ball. As long as the string would hold it, they should have the same period if you ignore air resistance and friction and all the other things that we normally need to worry about. At this point, we can rearrange this equation for gravity, or we can just plug everything in. We need to realize that if it's 5 swings in 16 seconds, then that would be more of a frequency. So the frequency here is equal to 5 swings in 16 seconds. And so our period, remember, is just the reciprocal of that. So it'd be 16 over 5, 16 seconds for 5 swings. If you take that 16 seconds and divide it by 5 swings, you should end up with about 3.2 seconds for the period. So we'll go ahead and plug that in. 3.2 is equal to 2 times pi times the square root of, we see the length here is already in meters, so that's good, 2.5 meters, and we're going to divide that by g. So we're looking for g. When you're done, you should be able to do the math that's here. Pretty simple to do. So you're basically, we just want to move the g here, but we've got to square both sides first and do some other things. So your g in the end should be equal to 9.6 meters per second squared. If you need help with this math, going from here to here, come see me during period 6 and I can help you with that. For the very last problem in this section, which number 62, says find the length of a simple pendulum that has a period of 1 second. We're going to use the same equation again. The period of a pendulum is equal to 2 times pi times the square root of L over G. And this time, let's go ahead and solve for L. So before we put any numbers in, let's go ahead and do our math for that. We have to square both sides. So we're going to say T squared is equal to 4 pi squared. And now we're just left with L over G. If I want L by itself, I need to divide both sides by 4 pi squared, multiply both sides by G. So L will be equal to T squared G all over 4 pi squared. Our period is 1 second, so we're just going to do 1 squared. Gravity here, we're going to use the more standard 9.81 instead of our easier 10 that we usually use. And we're going to divide that by 4 pi squared. If you do that math, you should end up with 0.248 meters or 24.8 centimeters. And that is the last problem in this section.